Okay, welcome Math 220, Linear Algebra. This is the last problem in the 2.3 section that was on the handout that I didn't get to. We were going to do that yesterday and today, and maybe we'll do it tomorrow, but I'm going to give you a precursor of this, and hopefully it'll save us time in class. So we're just supposed to prove that if A, B equals C, and that both A and B are invertible, then C must be invertible. So let's just go over some basics. If A and B are invertible, they're both square. So in order for them to both be square, if A is n by n, which has to be square, B has to also be n by n, of course, because those have to correspond and they have to be square. So what does that make their product? C must be n by n. So we know all three matrices are square matrices. That is a requirement for invertibility. But also, if A and B are invertible, that means A inverse A equals the identity matrix, and B inverse B equals the identity matrix. So we'll be using those facts. And so let's take that equation, AB equals C, and say, how are we going to use this A inverse idea, that there's an inverse that exists? So if we multiply by A inverse on the left, now by the way, this is commutative. With invertible matrices, of course, you can multiply on either side. But we'll multiply on the left here, A inverse. So we're multiplying AB on the left, which means we need to multiply C on the left by the same thing. So the inverse of A times A, which using matrix associativity, A inverse A, of course, is the identity matrix. So that is the identity matrix times B. And of course, the identity matrix times any matrix is just that same matrix again. So that should give us B is equal to A inverse C. And now let's use the fact that B is invertible. And if we multiply on the left by B inverse on both sides, I should probably switch pens here. B inverse on the left and B inverse on the left there, or the inverse of B, then what do we get on this side? We get B inverse B, which again is the identity matrix, an n by n identity matrix. And we get this B inverse, the inverse of B times the inverse of A times C. Well, using matrix associativity, that means that B inverse A inverse, these are both, of course, n by n, so that makes an n by n matrix. And it's multiplied by C, which we also know is an n by n matrix. So we can simply use the fact that two square matrices, when multiplied together, if they give you the identity matrix, if they're square, and in the book it's an ancillary from Theorem 8. If you have two square matrices, they usually use A and B. Let's just say D and E. If D times E is equal to the identity matrix, and D and E are both square matrices, then both D, I should say, if DE equals the identity matrix and they're both square, then both D and E are invertible. And in fact, it goes on to say they are each other's inverse. D will be the inverse of E, and E will be the inverse of D. And so basically we have that here. We have C is square, and B inverse A inverse is square, so two square matrices whose product is the identity matrix. That means we can conclude that C is invertible.